Hey Meteorology Lab students, welcome back. Let's get right into lab number one. Three kind of disparate things that we're going to be doing in this particular lab. One is looking at units of measure. Another one is looking at units of location. How do we find a spot on the Earth's surface? And another one has to do with time and time zones. Now, I will fully admit with this lab, this is like the least meteorology direct lab we're going to do. This is a lab that has a lot of background material that we're going to be using throughout the semester. So there's skills and knowledge we're going to gain here that will be useful for labs down the road that are more direct meteorology. So don't fret if it seems like we're not doing a lot of cloud looking at this lab, because we're not. We have a separate lab for clouds later on. This is again kind of background stuff to kind of get us rolling. And again, like I said, skills and knowledge that we need for a bunch of the rest of the lab. So let's jump right into this. So for the units of measure, basically the issue here is we have a variety of units that we're going to be using in a class in meteorology. We're going to have English units that most of you are familiar with, and metric units, which some of you are also probably familiar with. Science is largely done in the metric system. And as a result, we need to become more familiar with that, because we're going to come across a lot of data that is in the metric system, and we need to know how to convert back and forth between units into units that maybe make a little more sense to us. So, to help us with that, we have our conversion table here. This is table 1-1 from your appendix. And it's going to be really useful for us to help understand how we're going to do this. We're going to use and reference this table quite a bit. So what I want to do is just kind of run through this real quick, run through at least one or two examples here, and explain sort of how we go about this. So we'll start with this particular example. This is from your lab intro, so you can kind of follow along with that and with the table 1-1. So for example, let's say we want to know how many meters are in 3.45 kilometers. Now, some of you may know this off the top of your head. That's fine, but just bear with me here as I show you mathematically how to do this. So I have this sort of a several-step process I like to use for this. The first step is just write down what you're given, the first thing that you're given. In this case, 3.45 kilometers. So you start by writing down what you're given. Next, you go to your conversion table and you find something that relates to kilometers and meters. And if you look on your table, what you'll come across is that 1 kilometer is equal to 1,000 meters, or 1,000 meters is equal to 1 kilometer, either way. And we're going to write that here by putting the kilometers at the bottom and the 1,000 meters at the top. Now, the reason we do it this way is because kilometers is on the top here, kilometers is on the bottom here. And by setting it up this way, the kilometers will cancel. The numbers don't, but just the unit, the kilometers unit cancels. So that leaves the only unit left is meters, and that's the unit that we want, because we want our answer in meters. So we end up doing the math, 3.45 times 1,000, which we have here. And then our kilometers are gone, so the only unit we have left is meters. And then we have 1 on the bottom. So 3.45 times 1,000 divided by 1 is 3,450 meters. Right? So again, multiplying by 1,000, you simply move the decimal point 3 places. Divided by 1 by anything is the same number. So that's how you do that. Mathematically, that's how you set that up. Now, when doing this, you always want to make sure that your answer sort of makes sense. And if we have 1,000 meters in 1 kilometer, it should make sense that 3.45 kilometers should have a lot of meters. So it should be a relatively big number. And we have a relatively big number. So that makes sense. Our answer is realistic. It makes sense. For your exercises in the practice lab and the post lab, I want to see this set up like this. I want to see the units canceling. Again, if you look at the key for the practice lab, I have little lines crossing out the units. Anytime that I ask you for unit conversions, I want to see those units canceling. All right, back to step 2 here for a second. Let me just show you a way not to do this. I usually don't spend a lot of time showing you the wrong way to do things, but this is a common mistake people make. Let's say you got to this point here. We had 1,000 meters, 1 kilometer. If you put a kilometer on top and the 1,000 meters on the bottom, the kilometers don't cancel. And the unit you end up with is kilometers squared per meter, which I don't even know what that is. That's a weird unit. And you have the wrong answer. Right? So make sure again that when you set this second step up, that you set it up so that your units cancel from the top to the bottom. That's the key to this whole thing. All right, another one, real quick. Oops. So in this case, we wanted to find out how many kilometers in 3.45 meters. Again, this is straight from your handout. And so we start again with our meters on the bottom, meters on the top here, 1 kilometer per 1,000 meters. You end up doing the math. 3.45 times 1 is just simply 3.45. So we divide that by 1,000, and our answer is 0.00345 kilometers. And that makes sense. It's a small number. It should be a small number. But the key here is setting it up so that your units cancel from the top and the bottom. Sometimes you end up with just multiplication across the top. Sometimes you have to divide by the bottom. Just depends on the question. It varies quite a bit. Now, there are a couple other examples in the PowerPoint. I'm just going to let you run through those. And I want to jump ahead a little bit. All right, so this is your practice lab. So what I wanted to do is just run through 1 or 2 of these from your practice lab with you. Again, kind of show you how you can set this up. Let's do this second one here because the first one's off my board. So the second one is 25 knots. We want to convert that into kilometers per hour. So what we're going to do is we're going to start by writing down what we're given, which is 25 knots. And we're going to multiply that by something. Right? And we're going to have knots on the bottom, hopefully, and then kilometers per hour on the top. So let's go to our table and see what we have. So we're talking about speed here, and we have 1 knot is 1.85 kilometers per hour. Right? So 1 knot is 1.85 kilometers per hour. So we put the 1.85 kilometers per hour up here, 1 knot there, and then our knots cancel out. The unit that we're left with is kilometers per hour. That's what our question is asking for. And so now you just do the math. And again, if you have a calculator handy, you can do this. But it is 25 times 1.85, and the answer is in kilometers per hour. Okay. Off the top of my head, I don't remember what the answer is, but again, you have it in your key. But that's how you set it up. Again, the key is that you're canceling out these knots, and you're left with kilometers per hour. That's what you want. Okay. All right. Hopefully that makes sense. If not, just let me know. That's basically how you set up most of these problems. A few of them are going to be a little bit different. A few of these are just plug and chug kind of equations. Like temperature, for example, is just sort of plug and chug. And again, you have the formula in your handout about how to do that. So that's pretty straightforward. Next up is location. And we want to be able to pinpoint location on the planet. We'll do this a lot of times with storm systems where the center of the storm is, but also we'll talk about changes in weather or climate with latitude or longitude, things like that, mainly latitude. But basically, so latitude and longitude is a grid system that we have that allows us to find position on the planet. So for example, this is the handout you have in your appendix. You have the map of the Earth here, and then you have this grid system that helps you identify where things are. So you have the equator here And these lines that are parallel to the equator, those are your latitude lines. So you have north of the equator, south of the equator. These lines here are your longitude lines. And your 0 is what's called the prime meridian, which goes through Greenwich, England. And so you have your longitude lines going this way and your longitude lines going this way. So west longitude, east longitude. And they go all the way around the globe. So we have 180 degrees west, 180 degrees east. Add those two up, you got 360, you got a circle. And so it gives us a grid then, and we can pinpoint location anywhere on the planet if we know its latitude and its longitude. So again, it's like a grid system. So, for example, if you want to find out where you are in a grid system like this, like where's Waldo, if I find Waldo and I want to let you know where it is, it's awfully difficult to kind of explain or try to show you where it is on this where's Waldo thing. But if I put a grid system in here, let's say I would use letters up here and I use these numbers on the side over here, and I find Waldo, ta-da-ta-da, there he is, I can say, hey, you know what? If you look on yours at F4, right, F4, that's where he is. And so Waldo in this case is at F4. So that's just an example of how we can use a grid to pinpoint location very easily and quickly. So in this one, it's letters and numbers. On the Earth, it's latitude and longitude. And so there are some questions where you guys are looking up latitude and longitude and answering some questions on that, like on this question here. So, sorry, it's sideways. But, all right, so that's location, relatively straightforward, probably a review for some of you. The next one is a little weird, and that's looking at time. Now, there's no metric time. A second is a second, an hour is an hour, a day is a day. But how we report the time of day is a little different in science and meteorology in particular than it is perhaps what you're used to. First off, when we report time officially with meteorology, more often than not, we use the 24-hour clock format, also known as military time. Reason we do that is because with military time or 24-hour clock, there's no AM and PM. And that can get confusing. If someone says, oh, when did that happen? And you said 7 o'clock, well, is that 7 a.m. or 7 p.m.? And if you're writing something and you just say 7 o'clock, it's hard to know unless you put AM and PM. If you forget to put AM or PM, then you really don't know what's going on. So that's why it's really useful for us to use a 24-hour clock, because there's no AM and PM. So basically, with a 24-hour clock, there's kind of two things that we do. We start at midnight, which we write as 000 is midnight. And then 1 o'clock in the morning would be 0100. 2 o'clock in the morning, 02. In military time, you'd say, 0200, 0100, something like that. So you keep doing that until you get to noon, which would be 1200. And then at what you and I might call 1 p.m. in the afternoon, that's 1300. 2 p.m. in the afternoon would be 12 plus 2, which would give you 1400. 3 p.m. in the afternoon is, again, going to give you 12 plus 3 would give you 1500. 10 p.m. is 12 plus 10, 2200. So that's how you determine and write this 24-hour time. And again, the advantage of this is if you tell me, oh, there was a tornado and it occurred at 1400, well, I know exactly when that is. You don't have to, if you just said 2 o'clock, I would have to know whether it was AM or PM. If you tell me 1400, I know it was in the afternoon. Right? So that's the advantage of doing that, and that's why we use that in meteorology. Now, another thing that we'll see quite often, just to help clarify that that's what we're using, let's say you're talking about a weather event that occurred at 14:53, that would be, again, 2:53 p.m. Is the equivalent of that. Sometimes we'll put a little Z here at the end just to tell us that's what's called Zulu time, which is Greenwich Mean Time, which I'll get to in just a second. But anyway, you'll see that Z. So what does that Z really mean? Again, Z stands for Zulu, which is a shorthand way of just designating in time that you're talking about Greenwich Mean Time or Universal Time Coordinate, UTC. And this is where things get a little complicated. When we report a weather event, we often will report it not in the local time when it happened, but the time it was in Greenwich, England, when that happened. Now, it may seem like that's a really crazy thing to do, but it actually, in the end, makes things easier. So, for example, here's why we do this. Let's say there was a tornado in Western Australia, and it is reported as happening at, its local time, 2 p.m. in the afternoon. Well, if I'm here in Los Angeles, right here, I don't know, was that 2 hours ago? Was it 5 hours ago? I don't know, because I don't know how far away I am from Western Australia. I'm going to have to look up on a big table like this to figure that out. However, if this weather event in Australia, if the time given for it was not the local time here, but the equivalent time in Greenwich, England, here, this time zone, then all I need to know is what's the time difference between me and Greenwich. And it turns out, just so you know, for Pacific Standard Time, we are 8 hours behind UTC. And for Pacific Daylight Time, when we're daylight saving, we're 7 hours. So let me just take this a step further. Let's say you then hear about a typhoon in the Indian Ocean that's going to hit Madagascar here. And you hear weather reports, and they're not in the local time, they're in Zulu time. Again, here. So if both these weather events are reported not in their local time, but Zulu time, then all I need to know is this, is what's the time difference between LA, where I'm at, and Greenwich Mean Time. And again, it's either 8 hours or 7 hours, depending on whether it's daylight saving or not. If there is, really, really bad rainstorm, on the west coast of Peru, again, and it's reported as Greenwich Mean Time, then I don't have to look up what time zone this is, or what time zone it was in Madagascar, or what time zone it was in Western Australia. If it's reported as Greenwich Mean Time, I only need to know one time zone difference between me and Greenwich, England. So it sounds like it's more complicated, but when you're dealing with a lot of worldwide weather events, it makes it a lot easier if it's just reported in a single time zone. So when you see a time listed for a weather event, and it's, again, I'm just making up an event here, but let's say it's 2137 with the little Z, that means it occurred at 2137 Zulu time, which is again Greenwich Mean Time, this one here. So like I said, it seems a little like, why bother doing that? It seems like it's more complicated, and I realize, unless you deal with a lot of worldwide weather data, it sort of does make it more complicated, but we will come across weather data where we're going to see a lot of Zulu time. A lot of the weather data sets I'm going to give you, especially for Next Lab, they were recorded and reported as a certain Zulu time. So having an understanding, that's going to help you understand those data sets a little bit better. So anyway, you have some questions on those as well. Like I said, especially with the practice lab, you've got the key to help you sort of work backwards if you're having trouble with this, and help get you to understand better these time zones and things like that. Oh, I should say too, we also talk about the time zones as well, especially here in the U.S. With this table here, which shows you the different time zones for the U.S. And again, we have the Pacific, Mountain, Central, and Eastern time zones. So we have 4 time zones. What that means is there's a 3-hour difference between East Coast and West Coast. So you might have noticed sometimes with TV shows, they'll talk about, oh, it comes on at 8 o'clock Eastern, which would be 5 o'clock our time. Anyway, that's a little bit about time zones and time in general, how we report that. Hopefully that makes a little more sense. Work through those problems. If you have any questions at all, just let me know. Otherwise, I'll see you next time. Thanks, guys.